Hey everyone, let me just set up here. Yep, ADA and bolts here.
Yeah, I have software that the whole time.
Nice. Is it not showing? Oh, okay. So let me just duplicate this. Let's see. I'm on VGA, so. Build the satellite and then. No? Alright, so what are we going to do? Let's use another computer. Yeah. We're done with this one. Alright, so we'll talk a little bit about ourselves until this gets loaded. So my name is Luigi, and I'm here with Kyle. How this whole thing happened is that we signed up to then compete in this NASA's CubeQuest challenge. So this CubeQuest challenge is a challenge that you have around 15 teams are competing to try and get a ride on EM1. So we're not as lucky as those who already have a ride or have money, but we are definitely open-minded about trying to get there. So to give you an idea, we have this model from back in June. We haven't really updated yet with the new model yet. But yeah, so we're working on this Lunar CubeSat, which is a 6U, right? And we want to say that, first of all, we're very, very grateful to be here. I mean, this is our first time being at the AMSAT Symposium. And it's great to put a face to the names that we've been, just like corresponding with through email and over the phone, which is great. So let's step through. So then the people who have formed this team initially was Kyle and myself. And the core team has grown, and now we have nearly a dozen people working on this together of different disciplines. By the way, everyone has a full-time job, so you can imagine, right, that we're working on this stuff after work or just over the weekends, right? Okay, so the previous work, the reason why it's called Ragnarok is because the last satellite that we worked on was called Dellingr, and this was the summer of 2014, and this was over at Goddard. If any of you have ever worked there, then you'd know that Code 596, Chuck Claggett was working on this project, and this should be launching at the end of this year. So yeah, we made some minor news, which is great, really like that. I was working on the solar panels, and I was working on the actual control systems. And here's an idea of what Dellingr did. Dellingr had this boom, which is one of the very first to have booms. And they have the science payload, and you can see that this was the type of design where you have closeout panels. So you have this base plate and everything you close out around it. So getting to the point now, the one that we have right now, I'm just going to pass this over to Kyle real quick. Here's a picture of it, and Kyle.
Oh, it's weird to hear my own voice. Okay. Oh, closer. Oh, ooh, that's loud. Okay. Hello, everyone. Yeah, just talk about the motivation for this project we started, why we got involved with AMSAT. So it all started last summer when we were all interns at Goddard Space Flight Center. There was 4 of us, and we read the RFI for this CubeQuest challenge. And it was that time before the CubeQuest challenge was even announced that we decided we wanted to do this. This is kind of easy to jump into when you don't realize how insane amount of work it is. But we've come a long way in the last year. So Luigi and I met kind of at Goddard last summer. And so after we started putting together designs, surveying what technology is available, like is this mission possible, is it feasible? Because it is kind of pushing the technology of CubeSats further than they have been going. Because this mission requires propulsion, which is not even normally flowing. So this is like when we started talking to Jan King, that's how he got us connected with AMSAT. And so we were very, very glad to partner with AMSAT, although it took a year to come around to this, that AMSAT provides the radio and we're going to provide the rest of the bus. In addition to AMSAT, we have several partners. There's Emergent, who's doing our trajectory analysis. And we have this InnoSlate. We're doing very extensive systems engineering work using their software. And then we have Hammers. They have a ground station software. And so Georgia Tech is providing a cold gas system, which is also flying another flight from EM1 for the NASA mission. And Vanderbilt is listed. They're providing us radiation guidance. One of the things we identified pretty late in the game was that radiation is going to be a huge issue for this lunar mission. So the radiation environment when you're beyond the Earth's magnetic field is much more extreme than when you're around Earth. And it has come to the point where we are too risk averse to even fly any COTS flight computer that's available for CubeSats. So for this mission, even though we're buying a lot of components from other companies, we are going to be developing in-house our rad-tolerant flight computer and EPS, and also the structure.
Do you know the total dose?
I don't think. Yes, something. So we're using this software from ESA called Spenvis, where you can model your trajectory and get the dose.
Cream.
And Cream.
96.
96. Yeah, some number. All right. So what is the CubeQuest challenge? So NASA is looking at these cubes and they're saying, "Wow, this is actually becoming very capable." But they're not quite good enough for what we want to do. So we're going to put down $5 million in prize money and get all these people to invest way more than $5 million in developing technology for us.
That's how they work.
And so the mission is that you have to compete to win a flight on EM1, which Warhead already has, but we have to fight for our spot. And then you are left off not in lunar orbit. You actually have to have very high delta V propulsion to enter lunar orbit. And then the challenge itself is to transmit as much data as you can from lunar orbit. There's a 28-minute window or a 28-day window. So that becomes our mission objectives. So here's a picture of Heimdallr, who blows his horn at the start of Ragnarok. So we named our first CubeSat Heimdallr. So Heimdallr will first enter lunar orbit and transmit data at the highest bit rate it can, and because AMSAT are a wonderful partner, after we're done with our mission, it will remain in lunar orbit for AMSAT users to do voice relay. If you have the equipment to do that, it should be a lot of fun. So also, part of this challenge, there's 4 kind of ground tournament gateways in order to compete for the spot, and we've already passed the first gateway, and we were chosen as one of the top 5 teams for 3 available slots. So we feel pretty good about that, that we will actually get a chance to fly this satellite.
You don't mention the prize money?
Well, I said $5 million.
No, like the grounds.
Yeah, we won $20,000.
That's how we're going to get there.
So, all right. Here's just an overview of what is the SLS EM1. So NASA's Space Launch System is their new big rocket. It's supposed to eventually take people to Mars, but that's like a really long-term goal. So this EM1, Exploration Mission 1, is unmanned. It will launch up, then it releases the Orion module, which is the crewed module, but it will be uncrewed, and which will circle the moon and then come back to Earth. So that's their first unmanned test mission. And so the idea is that where we will be is there's the crew module up here, and underneath it they have this adapter bracket they call the MSA. And so inside that bearing ring, they arranged to have 12 slots in a ring. it can fit 11 6Us because one is used for the deployment mechanism and controller. Although we were told they're actually currently updating that. They're making it into 18 slots, but because of mass issues, they're probably going to fly 13 6Us on this first mission. And actually almost all the slots are now filled by various NASA missions or universities and private companies. And here's one cool thing. I like this scale picture. You can see it's about the same height as the Statue of Liberty, including the base. So pretty big rocket. So here's kind of our mission concept of operations. We're going to, so this is a chart that was given to us by NASA, kind of the details of what happens to the SLS before we're deployed. They go through their whole thing, have to do like the fuel blowdown, and it becomes totally inert, and then finally they deploy us. And so we're actually going to fly by the moon, going to have this huge loop around the Earth Sun L1 point and come back to the moon, and then enter an elliptical retrograde orbit. And then we have to, for the challenge requirements, you have to transmit these packets from between like 3,500 and 10,000 kilometers radius. So we actually have to add more delta V in order to reduce our orbit to this 10,000 kilometer circle. And so this chart details the timeline for that and the delta V cost. It's about 5 months to actually get to the moon, and but then we have another 2 months, 2.5 months in order to circularize before we can do the challenge. So this again, like, it drives our radiation concerns because we have this like 8-month mission before we even can start transmitting packets, which is our goal. And so this trajectory actually was developed for us from Emergent. And the reason for this trajectory is because for the SLS safety requirements, like, it's, this is their pride and joy, so they're not going to let you fly chemical propulsion, which is like really high thrust propulsion. You can just like directly enter lunar orbit. So we have to look for alternatives, which are all high ISP, low thrust alternatives. And so with 1 milliNewton of thrust, you can do this trajectory and enter lunar orbit within 8 months. If we were allowed to fly chemical propulsion, we could just enter lunar orbit within 3 days. I guess talk about the hardware.
Okay, talking about the hardware. So initially we were going to buy a lot of COTS parts, and like Kyle was, what Kyle was saying earlier is that if we're using the flight computer, the power supply, the wheels, and the star tracker, we would have to buy them commercially, but they are using the typical conventional processors, and we're looking for something that is rad tolerant. So think about it. You really have the 3 most important components are the power supply, flight computer, radio. And if those fail, then you just have a box flying in space, right? All this done for nothing, right? So it looks like we are now going to decide on which processor to use, but we are making our own rad tolerant flight computer. And so here you can kind of see that this is an old design. This is like back from June. And this is old. I mean, we're just flying through this. We work on this, every week we work on this. So originally we had the 4 wheels separated, but it looks like now we're going to integrate everything together. Pretty much the entire GNC stack we're putting together in-house. And we're forced to use 18650 batteries. That's just the only ones that are actually qualified. And yeah, so you can see down here at the bottom, we have a picture of U6 system, but we haven't actually finalized that yet. And we are definitely using an RF ion thruster. And then for the antennas, you have 10.5 down and 5.67 up, pretty much standard, right? And in terms of speed, you have 4.83 megabits per second. So that's a very low, a very conservative number. There's plenty of room to actually upgrade that. And yeah, so this is the platform bus that we have, and this is a model back from June. Let's step through. Block diagram, this is just pretty standard. You have your ACS system, the flight computer. If you didn't know, we're also using CFE, which is the open source flight software that's used even on these very big missions like LRO. And yeah, so here we have our pack, and we're going to have our triple set of batteries and whatnot, and then you have a communication system that we're working with AMSAT, we're working with Howie on that. And yeah, so this is a good view. This is very, very technical. I thought some of you might actually appreciate that. In terms of schedule, we're looking to then, we will have this delivered February 2017, right? So we have our own internal schedule that we're planning to have done PDR before GT2, which is Ground Tournament 2. And that's in February, coming up in a few months. So things are looking great for us. We're really happy about this. And let's talk about the cold gas system. So for the cold gas system, we're working with Glenn Lightsey, and Glenn Lightsey used to work at Goddard, and then now he became a professor at Georgia Tech. And we're looking at carrying 236 FA, which is just one of those cold gases, and we're just complying, you know, just trying to follow through and make sure that we then qualify as a pressure container and whatnot. So that's great, step through that. And then in terms of solar panels, I mean, that's like the first thing that probably caught your attention here. Probably like, wow, that's a lot of power, and those are triple deployables. And yes, that's what we're doing. We're looking to use Honeybee Robotics Gimbal, and you can really look at that and say, wow, that's a lot of cells. And yes, that's 108 cells. Triple junction, so we have room to scope down, but it looks like we'll be producing around 110 watts. We're just aiming at 100. So therefore, you know, we're sticking with the, you know, like the very common Vulcan springs and using a burn wire, and we're making our own hinges. And then in terms of the thruster, we are in the middle of choosing either Busick or some other. And yes, so it's a very similar system to Lunar Ice Cube, right? We know that this is the cutting edge. This is what will get us there if we were to use it. So we're open-minded about that. And then at the end of the mission, I mean, we could stay around lunar orbit, or we can pursue something different, which is we're looking to consider to copy the same type of orbit that Artemis has. So think about it this way: every time you look at the moon, you can just imagine that we would choose one of these libration points, which is L1, right? And we'd be able to stay there and have constant line of sight with the Earth. And that's the plan they plan to do afterwards. So when we hand it off, then there will be full access for your own transponder and for your voice relay. So I'll pass this off now to Howie. Hello, Howie. Good to see you.
So, just like McGuire in the Hume Center, AMSAT's got to sing for that sucker on this one. Part of AMSAT's mission here is actually to support this whole mission from point of track and telemetry control. So the radio, while it will be used as a transponder, its primary function is going to be to help determine location of this and do the range rate calculation, so that they can navigate the satellite as well as provide command and control for various operations. We've decided that we're going to use the same frequency scheme that's being proposed for the geostationary, 10 gigahertz down from 0.5 gigahertz up. And good reason for this, because amateur participation is going to be very, very important to the success of this project. As has been stated, the DSN network is already oversubscribed. Finding people with large antennas to help out with the receiving the telemetry downlink and helping us do Doppler tracking is going to be very important. There aren't that many large antennas around that we'll have access to. Relying primarily on the EME community to help, again, is going to be spotty. So if you look at the downlink station, the ground station being proposed by Dr. Cloth, and the sample of which is in the back, we're hoping stations that size in large numbers can help us with, particularly with the Doppler measurements. And we're going to need many Earth stations that size around the world if we can, specifically, especially in the southern hemisphere. It's going to be very important to help us do the attitude control determination. So by having very low-cost ground stations, receive only, that we'll be able to get this information back to help with the local determination will be critical in accomplishing this mission. So AMSAT and the amateur radio community as a whole are are going to have a very high profile in the success of this mission, and certainly elevate amateur radio in the general STEM community as here is how we can all participate in this. So one of the other side effects of this is that we're going to use equipment that's going to be compatible with the geo transponder that Geotech is building, so that the same equipment will be able to be used on both satellites. And hopefully the idea is to make this a more or less standard as other satellites in this category are built, that all the equipment will be able to move from satellite to satellite without having to go back and get new equipment every time. So it will be a one-time investment for the user community. Hopefully that will propagate users. This is a conceptual block diagram right now. Might be a little bit hard to read. And one of the key factors in the radio portion of this is going to be redundancy. I think one of the things we learned from AO40 that some considered a failure, but I always consider a tremendous success, was because despite numerous onboard hardware problems with that satellite, we did get a functional satellite that we could all use. And we did that because AMSAT flew many different components that were configurable in orbit, and they were, no matter what broke, we found a way to work around it. We're going to take some of that concept and get moved into this block diagram here. So what we have is that we have multiple paths, and this is actually multiple receivers. This is the analog section I'm showing here primarily. So we'll have both omni and directional antennas on the satellite. The reason why we thought about including omni antennas on here is because at initial separation, we're not sure what the attitude of this is going to be. And we may need to get in there and make some quick adjustments for attitude and control and some health things. And if the 10 gigahertz antenna isn't pointing towards Earth, well, we'll be lost. So we're putting a omnidirectional antenna on there that we'll be able to use. So that gives us a little bit of redundancy, and it'll have a separate feed path. But the way we're doing this is, rather than use switching, because again, there's an unknown there, when do we throw the switch, which antenna do we switch on? Both antennas will actually be connected at the same time and have their own individual RF paths, which convert down to a common IF, and then we'll have the filter out part of it. So we'll have a omnidirectional subband and a directional subband. These two subbands then will be combined and fed into the receiver. But I wasn't real comfortable with single receiver. So we're going to have two receivers. One of them will be a software-defined radio receiver, very similar to the GEO satellite. The other will be a really dumb and simple FSK receiver. The idea here is that, as Luigi said, this is going into a very hostile environment with bioradiation problems. We don't want to take the chance of having radiation damage to our SDR receiver and have a total loss of the mission. So we have a really dumb, simple hardware receiver. We may have an alternative. It won't be high speed, it won't be great signal-to-noise ratio operation, but if we throw enough power at it, it'll hear us. So hopefully, if the worst happens, we'll still be able to recover the mission. And we can switch between antennas just by changing frequency on the receiver this way. So if we tune the simple receiver to the omni subband, we'll receive on the omni. If we tune it to the directional antenna, we'll receive on the directional antenna. Okay, so let me get to this quick then. The important thing I want to get out of this is that we need help. And we're really appealing to AMSAT membership that if you ever thought you might want to get involved in building a satellite, we'd love to hear from you. This whole section on the right-hand side, on my penciled in block diagram, I just have one big block there, so a miracle happens here. Because we really need help with the SDR part of it, and just about every part of it, especially that part of it. Shocking or quiet?
I will speak for no one but me. Okay, so we're using the LPFE. Because of the complex protocol, we're using the ARM, etc. The same company that's doing the LPFE has another SDR, which was done for another company, and it has a PowerPC P2020, which is overkill for everything you have to do, and a Vertex 7. And this, they paid for the testing themselves, so I'm not going to tell you the number. But I believe the thing is sufficiently the radioactivity has gone down enough that they can get it out of the chamber now, but I'm not sure. And it had 0 single event latch-ups. Okay, so I'll be in Tucson Tuesday, Wednesday, Thursday, and Friday. I will speak to the CEO of the company and see what we can do. The other thing is, so that SDR also has a PowerPC on it, and it could do every operation you need. Okay, you'll have to learn how to do Cordic mathematics, which is trivial because it has no floating point processor on it, so everything's integer. But it's easy enough. And what you can't do, you can do on the Vertex 7. So this is a Vertex 7 with an analog devices, RFIC, and the thing is way harder than your requirements.
Thank you, Bob. Not as hard as figuring out how to do all this SDR stuff. So if you know how to do any of this SDR stuff, we'd love to hear from you. And if you're looking to actually have your own programming in space and can help do this, we can really use the help. If you're thinking of helping, email me direct, abqs@amsat.org. I'd love to hear from you.
AMSAT DL has a 30-meter dish, and both of them, they operate it.
We're really hoping that we'll get access to that and have them help. We certainly hope that our friends at Warhead, since they're going to be on the same mission, they're all going to have the antenna pointed there anyway. You know, it will really be a big help. Okay?
Okay, sorry. What? Okay, so yeah, so we have our own website, so it'll be RagnarokIndustries.com, and I wanted to say that that's even hard for me to read, and I have 2020. I'm sorry, guys. But thanks so much for your time, okay? All right, take it.